Alright, so let's have a quick read of the story that's going on over here. We have this civilian, Peter Pan, no, not Peter Pan, Peter Pan is walking towards the right, and we want to know how far he can walk until this string over here breaks. Now this string, there's a certain piece of information that's important here, and that's the 500 newtons. So what this is trying to say over here is that when the string here is being pulled with this much force, so the tensile force is 500 newtons, this will break, and we want to know when the tensile force is either 500 newtons or more. So to draw this on the diagram, what it's really saying over here is that the tension over here, or we can say that the tensile force that is pulling the beam or the plank over here has to be 500 newtons or more. And of course we equate this to 500 newtons for the critical case. And we want to label the other forces that are happening here. So maybe I'll just do it in another color since I drew in green over here. What's a good color? Maybe purple. Okay, so Peter Pan, he weighs 45 kilograms and he is acting down on this plank over here. I'll just draw like this. There's a 45G. Okay. We also have the mass of the plank, which is 20 kilograms. So that means the mass of the plank itself should be 20G. So we also have 20G over here. Now, before I keep going, let's clarify the distances of, or the positions of both of these forces. So for the 20G over here, 20G is the center of mass of the plank. So this will be 5 meters. And for the 45G, this one, so just line that up and use a different color for this one. And for the 45G, we're going to have, well, we don't know. So how about we say that this 45G has a distance of x. We don't know this distance x. And I'll do it from this little pivot point here because we're going to use that later on. It's just a lot easier to work with because there is a reaction force here that we don't know about. Yeah, some sort of reaction force. Okay. And from here, we want to see how far he can walk. Now, if you want 500 newtons over here, then this means that this system will still be in equilibrium with this 500 newtons. But if it's greater than that, it won't be. It will tip clockwise. So what we can do over here is, let's find out what the distance that Peter can walk to the right from the pivot point until it's 500 newtons. And if the distance is even more than that, then the force 500 over here would be greater than, well, 500. It won't be 500 anymore, it's something bigger. Okay, so we're going to sum the forces at the fulcrum. So we'll call this the point A. This is A. And sum of torques. And we'll say that it's in equilibrium while the string tension here is 500 newtons. Okay, so from here, let us suppose that going up is positive, going right is positive, going anti-clockwise is also positive. And over here, we sum up the torques around the point A, going from left to right. This tensile force here is 500 newtons for now. Okay, so 500 newtons anti-clockwise. So maybe I'll write the distance first. So 3 meters to the left and 500 newtons. Okay, but the next force that we have is, you can say it's the 45G over here, then this one is moving clockwise. So you can imagine it moving this way. And if it is moving this way, then that means it is negative. And we're going to have, what distance is that? So If it's 5 meters to reach the center of mass, then that means it's going to be the difference between 5 and 3. So this distance here is 2. So we have 2 multiplied by 20g. And the only other force acting here that actually gives it the torque is the 45g. The R can be disregarded since it's acting at the point where we take our sum of torques. So the 45g from Peter is, remember that we define this distance as x. So suppose that x is to the right of the pivot point, so this means that we have minus x, we're going clockwise, and his mass is 45. So a weight of 45g is equal to 0. Okay. And from here, we're just solving for x really. So x is equal to, now what I'm going to do is I'm going to chuck 45gx onto the right side. And what we're left with is 3 times 500 minus 2 times 20g, which was on the left, but I'm also going to divide by 45g, which was the coefficient of x. And this is the value of x when the tensile force in the string is exactly 500. And we're going to solve this on calculator. Okay. What do we have? We have 1500 at the top minus 2 times 20 times 9.8, and this is divided by 45g. 45 times 9.8, and this gives us 241. Oh, okay. That didn't make too much sense. 241 meters. Let's just retype this out. Bottom is 45g. So this gives us 2.51. Okay, that makes a lot more sense. 2.5 meters. Work with a few more decimal places since this isn't our final answer. Or is it? I think it is. So this is saying when x is 2.5, or approximately 2.5, then that means our tensile force in the string is 500 newtons. Okay, so what happens when x is greater than 2.5? Well, this means, now if we move back over here, we know that as Peter walks more and more to the right, so as he goes further and further towards his tip, so when x increases, so does the value of t. Because when x increases, the torque going clockwise would increase. So this one would increase. And if you want this system to stay in equilibrium, then the tensile force over here would also need to increase. So this one increases as clockwise torque. So clockwise torque increases. So you can imagine that the more mass that you have on the right side of this pivot point over here, the more stress this string over here would experience. So this means that when x gets bigger and bigger, or when it's above 2.5, then that means the tensile force will be above 500 newtons. And so to answer the question, string snaps. When Peter is 2.5 meters to the right of the pivot, to one decimal place.